what I normally do in this course, which is I'm going to get to a slide, and we're going to see if you guys know the material, okay? I really need like a response to do this, though, where like you guys give me some indication, okay? Because you really don't want me to sit here doing definition stuff if we can avoid it. You want me to work like problems, right? Yeah. Okay, so in these slideshows, you have all the material you could possibly need for everything, okay? But you shouldn't need all the connecting materials, right? You should already have those pre-read, right? And so, for example, we typically should be able to skip stuff like this right here. Like, what is an equilibrium constant? That's actually a general chemistry thing that you guys worked on for 3 chapters, right? And so, well, 3 to 4 chapters, depending on the book. So, the actual necessity of that should be relatively minimal, okay? Okay, so do you guys understand equilibrium constants? So an equilibrium is always dynamic, right? You have continuous exchange between the two. Notice this is the same sort of thing as you'd see for a reaction quotient. What's the difference between reaction quotient and equilibrium constant? It's whether you're at equilibrium, okay? So reaction quotient, which would be Q here, is not at equilibrium. If you calculate it out and it happens to be at equilibrium, then it is an equilibrium constant, okay? Okay, whenever you do this, this can be concentration of A, B. It's always products of reactants, right? So products are on top, concentration of C and D. They're to the power of their coefficients, okay? And then you have the concentration of reactants on the bottom, and again, their power of coefficients. Now, each quantity of this ratio is given as a concentration at standard state. So the concentration of the solutes is going to be expressed as moles per liter. Concentration of gases are expressed as bar. Note that there is a difference. If you have options, you can express Kc, for example, for gases. It happens sometimes. But if you have a mixture of them, this is how you express the concentrations, okay? Okay. What are concentrations of pure solids, pure liquids, and solvents? What would those concentrations be? Anybody know what unity means? It means it goes to 1. Okay? And so let's say this right here was a pure solid. It would have a concentration of unity. It would be 1 here. Okay? Any power of 1 is 1. And so it gets dropped from this calculation. You'll see this a lot with anything in water, where it like makes water as part of it, and it's in water, so it's a pure liquid. Okay? And so the concentration here would go to 1. Okay, so whenever you're looking at this, do you guys see how this is a big K right here? Anybody know why it's a big K? It's composed of reaction rates. So what's equal at equilibrium is the rate of the two reactions, going forward and in reverse, right? Okay, so those are going at an equal rate, and so a big K is composed of the rates of the reactions going in both directions, okay? They're composed of small k's. Everybody in biochemistry is going to experience this tremendously soon, okay? And all the knock-on effects from it, okay? You can think of a living organism as equilibriums that keep getting perturbed out of equilibrium state, okay? And never actually get to reach equilibrium. Okay. So when we look at this, keep that in mind. Now, if we look at these k's, what we'll see here is that if we have a k prime, that is 1 over k. Okay? So that's the inverse, the reciprocal of it. If we have 2 values that multiply together for the individual equilibrium constants, we'll get a third value. So if n reactions are added, the overall equilibrium constant is the product of n individual equilibrium constants. let's go ahead and try this real quickly. We have an equilibrium constant for this reaction here. It's called Kw, of course, and you've all probably experienced this a few times, right? 10 to the negative 14? Okay. 10 to the negative 7 times 10 to the negative 7, right? For a neutral solution, typically. So that's actually the value at 25 degrees Celsius, by the way. Any other temperature, it actually is slightly different. So the neutral pH of water actually changes depending on the temperature, in case you're curious. Okay, so given that this right here, KNH3 equals this for this reaction, what will be the K for this reaction then? Notice that this reaction is actually a combination of these two reactions. Okay, so you can add and subtract those two reactions. Now, notice I gave you a 1 over K value. If we flip products and reactants, what would happen to this? Flip, right? It would be 1 over K. Okay? Everybody okay with that so far? Okay. What would happen if we were to, say, add new things in here and subtract new things? Well, these would end up being multiplications, wouldn't they? Okay? And so you always do an order of operation different. Now, if we were to take these and multiply these all through, what would happen to the powers here? So if this had been 1, 1, 1, 1, if we multiplied everything by 2, 2, 2, 2, what would happen to the powers? Square. Yeah. So we'd square that K one way. Okay, everybody start adding those together. First thing you always have to figure out is which one is backwards. There is one that's backwards. Okay, everybody got it to the part where you'd actually do the math? Let's go forward then. Okay, so our KW one is the correct direction. We don't have to multiply anything. This one's a little bit easier. Okay, and so this one we have to flip though, don't we? And so we take 1 over that KNH3, and we have to do the reciprocal of it because we flipped the reaction. Our products and reactants have been flipped. The next thing we need to do here is, well, we need to take these two values and we now need to multiply them together to get our new K value, our new equilibrium constant. And so we're going to multiply the KW times 1 over KNH3, and that's going to give our product here, our new K value. Everybody good with that? Did I lose anybody? Yeah. Okay. So let's talk a bit about equilibrium thermodynamics and kinetics, okay? We keep matching my chemistry 103, by the way, which is so weird. Like nothing to do with each other usually. So enthalpy, everybody remembers enthalpy, right? That's delta H. Some of you have had a whole lot of enthalpy lately. So delta H is positive, endothermic. Delta H is negative, exothermic. Negative meaning heat is being released, right? Positive means heat comes into the system. Everybody good with that so far? Okay. Now, when heat's absorbed or released, that's the enthalpy. When we have dispersal of energy into molecular motions, i.e. more states it can be in, that's going to be entropy. Okay? And we calculate these independently whenever we're looking at the thermodynamics. And they independently contribute to the equilibrium constants as well. Now, this right here is standard enthalpy change. That's delta H naught. That's absorbed or released when reactants and products are in their standard states. Not prime, by the way, would be physiological states typically, or a perturbed state. All right, So this right here is entropy change. So when a chemical or physical change occurs in a reversible manner at a constant temperature, the entropy change will be equal to the heat absorbed divided by that temperature. Okay? The best way to probably understand entropy is you've probably been told randomness. Would that be correct? Okay, have you guys ever been told microstates? Did that ever come up? Yeah? In PChem? Okay. So what microstates are, think of it like you all arranging yourselves in the desk here, right? So this would be one microstate right now. And if one of you is to then move into a new desk combination, that'll be another microstate. Okay? And so our number of possible microstates are the measure of randomness. Okay? It's just a better definition that you can truly understand randomness to some degree. Okay? And so the more microstates that exist, the more randomness, the more entropy. Right? The less microstates that exist, the less entropy. Now, it's very important to account for temperature in this because if we were 0 Kelvin, right, and they're always in Kelvin, never degrees Celsius, you always do this in Kelvin, okay? What would happen to our possible states we could be in? What if I nailed you all down to your seats here and you couldn't move? Could you change desks? No. So if we remove all the random kinetic energy in a system, we will nail all the particles down and they will only have one microstate they can be in. And that means entropy falls to 0. And that's why you have to have that directly related to the temperature. That's because temperature is randomized kinetic energy. To have rearrangements, you have to have some sort of kinetic energy, motion, right? Okay, is everybody good there? All right, so again, when you have a greater entropy than the products, a positive delta S, that's going to mean you are increasing your entropy. When you have a negative delta S, that's going to mean you're decreasing your entropy, okay? You always have to pay the piper. That's what engineers usually call that. And so entropy of the universe always has to go up, okay? It can never even stay constant. It always has to go up, right? Now, having said that, that does not mean we always have to have increasing entropy in our system. Okay? We can increase the entropy somewhere else, right? Which is oftentimes how you get things to work. All right, so Gibbs free energy, delta G. This is going to be how we balance these two things, the delta H and delta S. You will notice that both delta H and delta S are actually heat flows. Okay? We've just taken heat flow. This one right here is just reversible heat flow over temperature, right? And then we've taken heat flow with constant pressure, and that's enthalpy. Okay? And so ultimately, these are both measures of heat flow. Okay? It's just, there are different concepts of heat flow, different concepts of randomized kinetic energies. Okay? All right, so delta G equals delta H minus T, temperature in Kelvin, times delta S. Now you'll notice here that this right here, if this value is negative, it will contribute to being a negative delta G, right? If this value is positive, entropy increases in the system, then it is going to contribute to a negative delta G, isn't it? Okay? If T is 0, because we're at 0 Kelvin, this entire term drops off, because you no longer have other microstates. It's one microstate. Okay? And so entropy goes to 0 as well. All right. So, now, does anybody have any questions about this so far? Did I lose people? Delta G gives free energy. This is a measure of spontaneity. Okay? Are you going to spontaneously change to a new state? Are you going to spontaneously change without adding energy? Okay? And so if your delta G is negative, what's going to happen eventually? That's going to happen eventually, right? If delta G is positive, then it's going to happen in the reverse direction eventually. Okay? It will never go on its own. You will have to put energy in. Okay? Now, what does delta G equals 0 mean? It's at equilibrium, yes. Or another way of saying that is neither way is spontaneous or both ways are spontaneous. Okay, kind of depends on what you're talking about. But in chemistry, typically it means both ways are spontaneous, which is equilibrium, right? Okay. So notice that this directly corresponds to equilibrium, doesn't it? So we see K here, that's the equilibrium constant, equals e to the power of, and that's negative delta G naught here. So standard conditions delta G. This is over then RT, which is the gas law constant, in the Kelvin. Okay. Okay, does anybody have any questions so far? So what does that tell you about K is less than 1, by the way? Which is favored if K is less than 1? So if K is less than 1, so products are always over reactants, right? Okay. And so going, the products are disfavored, the reactants are favored, right? Or another way of saying that is that, yes, the reactants, it spontaneously goes backwards, okay, to the reactants. If we have K is greater than 1, then what we know is that the forward reaction would be the one that's favored, right? That would be a negative delta G, forward reaction's favored. Or another way of saying that is the reverse reaction is not spontaneous. Or another way of saying that is if we're at an equilibrium, we're eventually going to end up having more products than reactants, right? All right. So Le Chatelier's principle. Everybody remembers Le Chatelier's principle, right? Yeah. So if you disturb an equilibrium, the direction in which the system proceeds back to equilibrium is such that the disturbance is partially offset. By the way, this is why buffer systems work. They're equilibrium systems that you disturb, and so they try to reset. Okay. The concentration here, we place the stress by increasing this concentration here. What are we going to do? Well, we're going to consume these, make some product. Once we have more product, it's going to want to try to go backwards in this equilibrium, right? And so it's going to then fight our directional change. Okay? And so that right there is an equilibrium under stress. Okay. Another way of saying this, if we put more of this species in, it's going to go this direction. An easy way to think about these is actually by thinking about a bottle of water, right? So like if you tilt it one direction, it causes the reaction to go towards that direction, opposite direction, right? So if I go up on this side, the water moves over here. Okay, now reaction quotient is just this exact same formula. And what that tells you is that you can use the reaction quotient to figure out, number one, if you're at equilibrium. If Q equals K, then you're at equilibrium. Okay? And the second part is you can figure out, well, which direction would we go to reach equilibrium? So for example, right here, we've placed stress that this is going to move towards products. And what we would see is that our Q is going to be less than K because this concentration is increased right here. See that? That make it a smaller number. Divide by a bigger number, smaller number.
Is Q just like...
It's the exact same formula. Products over reactants, the power of their coefficients. It's just not at equilibrium.
Okay.
So you do the exact same calculation, just not at equilibrium. Okay. Does anybody have any questions about that? Now, how does this relate to heat, by the way? Well, you can list heat as a reactant in product, right? So if you're endothermic, that's going to be as a reactant. Exothermic as a product. And so you can use these same principles to help you determine the direction heat would cause an equilibrium shift. Now, please note in actual real-life chemistry, this can be a little misleading, okay? So let's say you have a reaction where removing heat would favor products. And you just keep removing heat, more and more ice, colder and colder. What's going to happen eventually? Will you just get this reaction making all products? Okay, there's a second term, and that's kinetics, right? So when you have a reaction, will it spontaneously happen? In which direction will it spontaneously happen, right? But I've never said anything about how long it takes to happen, right? So when you look at it like a tank of gas in your car, it spontaneously burns, right? Everybody knows that. Okay. Does anybody know what happens to a gasoline in your car when you leave it for like a year? No? Okay. It spontaneously reacts with the atmosphere. So it oxidizes, it gums up in your engine. And if you like try to run your engine, it'll gum up the workings and it's awful. You have to like take it apart and flush everything. It's really, really, really bad. So if you ever leave a vehicle for a while or you think the vehicle's been sitting there for months on end and not being used, take out the gasoline, siphon it out, and then put new gasoline in. Okay? Because you'll destroy the engine. You can get it fixed, but it's a hell of a thing. All right. So the oxygen is oxidizing that fuel.
Sorry, going back to the last line. So the first one is a phase increase, that means the product that.
Yes. Yes. So like if we added heat here, this is going to favor products. If we took heat away, it's going to favor reactants. Does that make sense? Okay. So has anybody ever heard of the Haber reaction? It's a very common reaction to produce the nitrogen that you need for fertilizer and a few other things. But it is a reaction that is exothermic, very exothermic, okay? And it has a problem that it produces so much heat that it's actually an equilibrium reaction, and the heat actually causes it to drive itself backward into reactants. And so you end up actually getting a spiral where it can get so hot that it actually melts things and blows up, but also that it gets so hot that you can't get any products anymore. And so they cool that reaction. Now, the other part of this we need to discuss then is that, well, what speeds up reactions? Usually heat, right? Okay. And so remember that in equilibrium, there are going to be thermodynamic predictions. We have no kinetic prediction at all we've made. We've talked nothing about speed. The Grand Canyon was spontaneous in its creation, but it took hundreds of millions of years to happen, right? So it can be spontaneous, but incredibly slow, okay? There are hills with rocks up on the top. Spontaneously, that rock's coming down, right? But some of these hills are 1 billion years old. The rock still hasn't come down. Okay? So, again, these things have nothing to do with each other. Please disconnect them. Now, kinetics is going to calculate what must happen for a system. It's going to calculate how fast something happens. So it's going to be the rate reactants are used over a time frame, or products are made over a time frame. Now, again, remember, large equilibriums does not imply anything about how fast a reaction is. Doesn't matter how large the equilibrium is. Okay? It can be incredibly spontaneous, just the most spontaneous thing in the world, and it could take 1 million years, right? The equilibrium are going to be dynamic systems. You'll have the forward and reverse reactions, and they're going to occur simultaneously. And so a dynamic equilibrium looks like this. And so what was equal in an equilibrium? Well, it was always the rates, right? The rates were always equal in an equilibrium, not the amounts of product and reactant. Okay, so this is actually a kinetic regime right here. This is, you guys have all seen this figure where it's the two different things. So you have the reaction running forwards, and then the reverse reaction establishing as you make product, right? And then you've all seen it where it comes to the same point, and that's your equilibrium, okay? You've probably never thought of it like this, like I'm going to frame it. This right here is the kinetic part of the reaction, okay? It has a certain speed. So at this point, your rate right here is very high because you have a lot of reactants. As our reactants get consumed, our rate tapers off and gets lower, right? And then as products are made, our rate in the reverse reaction goes faster and faster and faster because we are increasing concentration, right? And then eventually the rates become equal, and that is the equilibrium portion, okay? So this is kinetic, this is thermodynamic. Is that making sense? Okay. So let's talk a bit about solubility products. KSPs, there are a bunch of different K equilibrium constants. There's Ka, Kb, KSP. Okay? There's actually a lot more. We don't usually encounter a lot of them. Now, KSPs are called solubility products. And so they're going to be that equilibrium constant for the reaction in which the solid dissolves to give its constituent ions in solution. Okay? It has to be something that can break up, though, for it to be a KSP. So notice that that's a dissolution constant, okay? The process of dissolving. All right. Now, what do you notice about the KSP here? As you know and define more and more things about the system, what happens to the math? It's easier. As you define more things about the system and have more limitations on the system, your math will always get easier. Okay? So a KSP has some of the easiest math because you always have on one side a pure solid. And so that's divided by 1, right? Everybody okay with that so far? Okay, you can find a bunch of numeric values in Appendix F, by the way. Now, a saturated solution, this is going to be an equilibrium with excess undissolved solid, right? How much undissolved solid? Based on the equilibrium, right? So whenever you have a saturated solution, it's always in equilibrium. And your amount of solid at the bottom, does that actually matter when it comes down to this equilibrium KSP? What if I have a trillion moles? Okay? Man, I have a planet. There's a little puddle of water. Is that going to change anything about the amount of sodium chloride in there? In that puddle? I made a salt planet. I put a little puddle of water on it. Is that water going to get saltier? Is there any term in here that shows solid? Not at all. Absolutely nothing. So the KSP, which is more temperature dependent, a few other factors, that will change it. So, like changing temperature, yeah, sure. But my amount of salt actually dissolved, no effect. Doesn't matter how much solid I have in there as long as I have hit the saturated point, okay, where no more of it can dissolve. And so whenever I'm saturated solution, that means I have the maximum amount possible dissolved, right? If you ever see a saturated solution, you can always tell because you have the liquid. They've been in a steady state for a long time. And then you have the solid at the bottom, and it's not dissolving. That's a saturated solution, and it has the maximum amount dissolved. And that's always this right here, which is the KSP. Okay? It's actually a cool trick you can play if you need to get really accurate concentrations, because the KSPs oftentimes for most salts are actually quite accurate. And so you can actually just make saturated solutions and then dilute them down later. Yeah. So kind of a neat trick. You can also use it if you have something hygroscopic and it picks up a bunch of water. Yeah. All right. So does anybody have any questions here? Okay, so let's use the solubility product real quick. What is the concentration of mercury in the equilibrium with 0.1 molar KCl and excess undissolved mercury chloride? So what we can get here is we can actually take our KSP. We can look that up in a book, i.e. the appendix. I'm going to see F, right? Okay. We can rearrange these. So we put chloride, which is the common ion here, right? Chloride on one side. And then we have our mercury on the other. Now, let's say that there's a large difference. See, this KSP is 10 to the negative 18. What does that tell you about how soluble that is? Is that very soluble? It's not very soluble. Versus KCl, which is very soluble, right? So that's going to be dissolved completely. And so what we can do is we can actually take our KSP here. We can take our 0.1, which is the concentration of chloride here. Now, technically, this should be plus the concentration of this one, right? From our equilibrium. But this number is very small, right? So if we take a 0.1 and we add 10 to the 10th, negative 10, would that change that number? Not at all, right? And so we can assume this as our number here, take it to the second power, and solve, and we get our answer out. Typically, the cutoff for this would be 5%. In analytical chemistry, it's usually lower. You usually want something more towards 1% or 1,000th. It would depend on what your uncertainty is going to be. Okay? But notice that this is 10 to the negative 16. If we took this and subtracted off by 0.1, off by this 10 to the negative 16, will it change anything? No, our math's going to be the exact same, right? Okay, does anybody have any questions about this so far? Okay, we'll try to work some of these problems next time. We'll see if you guys understand things. And then what we'll do is we'll spend a little extra time on that if we need. If not, we'll go on to that. Yeah, sure.
I haven't talked to Olivia or Austin. Is there any way we can rob the due